Hi, I'm Sean, and this is the first part of a series on robots, operating systems, and a robot operating system. In this one, we'll be talking about some popular paradigms, or ways of thinking, about robot autonomy. So, I've got a question. Are you a robot? Probably not, but let's pretend that you are. And you're a robot whose programmer has tasked you to fetch a coffee cup from the other side of the room. Let's work through this problem. So first, what are we going to need to do? Well, we'll need to find the coffee cup and figure out what is in between us and the coffee. Second, we will need to plan about how to get through those surroundings to get to the coffee cup and bring it back. And then we'll actually have to go and execute that plan. So these three steps fall into a paradigm that's popular in the robotics community called the sense, think, act loop, where you sense your surroundings, think about how you get through those surroundings, and then act on that plan. And this happens continuously because sometimes the environment changes and you need to resense, rethink, and react. And depending on what community you're from, you might also be familiar with a similar concept called the OODA loop, or observe, orient, decide, act. So to bring a bit of imagery to this loop, first you've got the environment, which feeds into your perception, your sensors. So you have those things that you sense, and you feed this into your localization, where you're thinking about where you are and planning on where you want to go. Then you act, where you take that plan and execute it, move around, moving through your surroundings. And as you move through your surroundings, what you sense changes, and then what you plan changes, and then what you control changes. So another paradigm we're going to talk about is guidance, navigation, and control. And you might be familiar with this if you're from more of a vehicle-oriented community such as aerospace engineering. Guidance pertains to determining where you want to go, what trajectory do you want to take. Navigation is about where you are. Where are you in terms of position and velocity? And then control is about how you get to where you're going. How do we activate our thrusters or our wheels and actuators to actually get to where we want to go? So these two paradigms we talked about actually can go hand in hand. So I've expanded our loop from earlier, and now let's start with the environment. So we're in the environment, and it's feeding into our sensors. We're sensing. This feeds into our perception, which helps us make sense of what we're sensing. And then this goes into localization, or figuring out where we are. Localization is more of the robotics term. Navigation is more of the aerospace term. Then you're planning on where to go. Planning is more of a robotics term. Guidance is more of an aerospace term. And then you've got control. How do you actually manipulate your actuators to execute that plan? And then again, this feeds back into the environment and the loop continues. So now that we've talked about this loop from sensing to thinking to acting, we might want to think about how we can divide up some of these responsibilities. And one way of doing that is called the backseat driver architecture. So the backseat driver architecture involves having two systems, a front seat and a back seat, where the front seat deals with, say, low-level control, where it takes in, say, a desired heading and speed, and then it tries to achieve it, and it can report out the achieved heading and speed. That goes into the back seat. The back seat does, say, more things that are a little more taxing, higher level autonomy, perception, things that might need a GPU, things that are harder to execute in real time. The front seat tends to be more of a real-time system. The back seat is not as constrained by time. And between these, you can end up having something that's more robust in terms of control, but also more powerful in terms of having access to that higher level of computation. This is actually a concept that is heavily popularized in the autonomous underwater vehicle community, specifically, say, the IVER 2, which is one of the first papers that you can find about this idea. So, to contextualize this idea in our loop, we've divided up the responsibilities where the front seat is highlighted in green and the back seat is highlighted in aqua. Now, we have a bit of overlap between the sensors and perception. Really, in robotics, nothing is ever quite so clean as this loop. You have things kind of skipping steps or maybe talking back. There's feedback. But overall, this is a way you might actually see the communication divided in a backseat driver system. The last concept I want to talk about is keeping it simple, stupid, which is less of a robotics and more of a general engineering idea. Simplicity is important. Complex things are hard to understand, hard to debug, but simplicity in itself is a bit of an art, and it has many dimensions. Simplicity in one way often results in complexity in another. Let's say, for example, you're working on a software architecture, and you're thinking about keeping everything all in one folder. And that might be good, it keeps all of your files together. But what happens when, say, other things are using just parts of your program that you're developing? It might get more complicated because you have to ship the entire bulky folder when all you need is one little part. So in one way, it's simple that it's all amalgamated in one place, but it's complex in terms of you're not able to get just the specific thing you need. So because simplicity is multifaceted, you really just have to try your best in terms of balancing your implementation with simplicity now, so you can actually get something done, and simplicity later, so you make an architecture that is not a pain to rework when your project has expanded and you're working with multiple people and there's a lot of moving parts. It's an art, and I don't have any particular advice, it's just something to consider. In the next one, we'll be talking about operating systems and how to use them.